Hello. Thanks for joining us today at the Charge Virtual Conference on EV engineering. The topic of this session is EMC issues for accurately measuring electric powertrains, and it's brought to you by HBK. There will be a Q&A session after the presentation, so please use the Q&A button on your screen to submit your questions at any time, and a recording of the presentation will be available to view on demand afterwards. And you can visit the session's registration page to find that link, and also a link to download the presentation slides. So please welcome our speaker, Mitch Marks, Business Development Manager at HBK. Welcome, Mitch.
Thank you so much, Chris, and thank you to everyone for joining. As Chris mentioned, the title of the session is Overcoming EMC Issues for Accurately Measuring Electric Powertrain. For those of you who do not know HBK, we are a test and measurement conglomerate. So we sell sensors, data acquisition systems, and software. And one of the most common issues we have, especially on the electric powertrain side, now this is structural or electrical measurements, is EMC generated by the inverters and the motors. So I wanted to do a session today really focused at test engineers and technicians on how to reduce EMC, how to understand EMC, and what to expect in some future issues. And then we're going to go over some HBK solutions for overcoming that. So I'll save the fun part, the HBK part, for the end, and let's jump into it. So as I mentioned, HBK makes a variety of different test and measurement equipment. But today, kind of the things of interest will be sensors. So we make torque sensors, current sensors, load cells, strain gauges, accelerometers, data acquisition systems. This is our eDrive power analyzer and data recorder for really looking at the high frequency inverters and motors. And then software for analyzing the noise and vibration, the efficiency, or just looking at the control type signals. And we've done some sessions in the past on, I think, all three of those topics with ChargedEV. So please go back through if you're interested. But we do 5 things particularly well for measuring electric powertrain. We make it really easy to measure electric and mechanical signals. We make really fast and accurate efficiency measurements. We're expandable to really high channel counts, and we allow you to future-proof. So if you're in agriculture or aerospace and you have a little more complex of a system than you might see in automotive, we really have some nice solutions for you. We record data and give you the ability to see what's happening in your system. And this kind of plays into the EMC world, because to understand EMC, you need to see it, you need to feel it, you need to look at the frequencies. And then we offer real-time calculations and feedback. And this is for integrating into a test stand or operating hardware in the loop. So we got those 3 things: sensors, acquisition, and software. And then this presentation will feature some of our products, but we also have local support and training in a lot of the major markets. So that's my sales pitch for now. We see ourselves as 5 things in one package. We're data acquisition, so we record data so you can see your signals and start to understand any issues you might be having, troubleshooting, EMC, EMI. We're very accurate, so we allow you to do really precise power analysis, to understand those power flows, to understand the efficiencies. We record the data and we let you see it. So we function as that oscilloscope. We log data for things like temperature, CAN bus, mechanical signals, and you can view all of those in our software. And we have a nice API and post-processing software so you can do your efficiency mapping. So you can look at your DQ0, analyze your phasers, or just do power analysis. So let's get into the interesting stuff. Quick agenda. We're going to go over EMI background, electromagnetic interference background. For those of you well versed in this, please be kind. It's not my area of expertise, but the measurement of it, I'm pretty savvy with. So please bear with if this is a refresher, or share with your colleagues who might not know this as well. We have new EMI issues that are evolving with these high battery voltages, these wide band gap semiconductors, silicon carbide, gallium nitride, cabling best practices, sample rates, and filtering. Because a lot of times you're going to undersample or use the incorrect filters because you think you have noise, when actually you need to really reevaluate what you're doing. And then we're going to go over some fiber optic measurement tools that HBK is coming out with that should help with these problems. So a little background on EMI. And I apologize, guys. I'm overcoming a cold, so if I'm coughing, I really do apologize. So EMI in its simplest form is electricity from one source interfering with a signal. And I always like to go back to when I was a kid. For the under 30s, I apologize. The idea of an antenna television might be foreign to you. But if you were watching TV or the radio and you had a really crystal clear screen, and then mom turned on the vacuum, or there was a lightning storm, or you had a car go by with a funny spark plug, you might get this crackly static in the screen. And this is really EMI at its finest. We have a electricity source from somewhere else interfering with a signal. In this case, the signal is the television. So that's the simplest form. And what we see is that we have a source of interference. That's our spark plug, our vacuum, our lightning strike. And I'm sure somebody in the comments will put something that they fought as a child. And then we have the sink of the interference, and that's going to be the television. And the interference can be inductive, galvanic, radiative, or capacitive. And we're going to dip into these a little further just to go over the background. But a signal or an electric source interfering with a signal. So we have the source of the interference and the sink of the interference. And that's the key takeaway from this slide. Galvanic coupling. And I'm not going to read through all of these, but this is really a electrical connection between the sink, in this case, my measurement, and my source. In this case, my, maybe my motor or my inverter. So we have this measurement and its measurement cable and maybe the measurement device that has some sort of ground loop or physical connection to the inverter, to the motor. And this really happens when we have a ground path that could be shorter across another circuit. And this is going to induce noise in the common path. So again, this is getting a lot into the grounding and those kind of ghost hunting that many of you have probably done and struggled with. The dependencies on this is the cross-section of the connection. So how much resistance is in the connection? If that's a low resistance connection, if it's a better path to ground than ground, you're going to get interference. The length of the connection, which again plays into the resistance. The resistance of the wire itself. Am I connecting this with string or is it copper? And the solution is really finding a better grounding tree, looking at your grounding plane, finding those low impedance paths to ground and correcting them. Galvanic's not going to be as much of an interest for today, but it is certainly a problem, and there are some ways to overcome it. Inductive coupling. This is I have a current carrier, in this case maybe my inverter cables, my three-phase inverter cables, that are creating a magnetic field. So the motor-inverter combination is creating a magnetic field, and my measurement line over here by RA is picking that up. And it's basically the transformer effect. We have a one-to-one transformer where we're creating a signal and we're picking it up in the signal line. Now, if you have loops of cable in your signal, now you have a better transformer. You're going to pick up more signal. So we'll get into this a little further, but the dependencies of this are DIDT. What is the frequency and what is the current level of the signal? What is the current amplitude? What is the distance between these cables? What we'll find is that this is a 1/R dependency. So the further away these cables are, the less interference we're going to have. It's going to be a common theme today: cable distancing, cable layout. Are these cables running parallel together? Are they running at 90 degrees? This gets into our kind of basic electrical engineering for circuit layout. And solutions: shielding, eliminating parallel paths and loops. Don't have loops. Every time I walk into a lab and I see loops, I want to die. Distance between cables, it's that 1/R squared. And then copper cabling. Eliminate copper cabling. This will be another theme we come to at the end. This is a way we can reduce that interference. Because again, high current, high frequency, coupling to a measurement line. Capacitive coupling. Now this is we have charge on the current carrier jumping over through a capacitive coupling to the measurement cable. This is now a frequency of voltage level and frequency. So we have this dVdt. We have a voltage changing in a short amount of time. We'll see this a lot in our future problems. Distance between cables. This is another common dependency. If these are right next to each other, running in parallel, they're going to have a close coupling. We're going to have charge jumping. We're going to have EMI. And then the cable layout. Again, rather than having parallel paths, we want to have 90-degree angles. Solutions, good shielding, eliminate parallel paths, distance between cables, and eliminate copper cabling. Because if one of these is not copper, we don't have that jump. And lastly, radiation coupling or far field coupling. This is actually an interaction of the electric and the magnetic fields, and it's radiated over a longer distance because we get that, kind of two waves interacting. This is now a dependency of current amplitude, voltage amplitude, and frequency. So we have dI/dt and dV/dt. And now this only has a distance of 1 over r. So this means our distance is even further that it will transmit. So the attenuation is a longer distance. So this is another source of noise. But the solutions are the same. Cable layout, distance, shielding, eliminate that copper. Because if there's no copper, there's nothing to couple to. So now you're all experts in EMI, and for anyone who wants to correct me, I'm always willing to take notes because, again, not my area of expertise. But what we end up with is these two equations I kept coming back to, and I'll touch on these a little more. But I equals C dV/dt, so the change in voltage over the change in time times the capacitance of that coupling is the induced current. That's the EMI current. The voltage, the inductance of the cable, again, that's a property of the cable, a property of the layout, times dI/dt, change in current over the change in time. So a voltage level, current level, frequency. These are three things that the engineers are going to give to you. They're not going to change that. We're making way cool advancements. We're doing all this cool tech. These things aren't going away. So we need to look at how we can reduce these things. And it's by eliminating parallel paths, by increasing the distance, and by really looking at our shielding. And I've mentioned this a few times, but what if we eliminate those copper paths? And we'll come back to that at the end. Now, nobody has ever had a lab that looked anything like this. I'm sure nobody in this audience has ever seen anything where we have loops of cable. We have wires everywhere because now we have 3 phases of voltage, 3 phases of current, DC, torque, speed, voltage, temperature, CAN bus, But there's a lot of sources for noise. There's a lot of antennas. We have an inverter down here kicking out a high frequency, a high voltage, and a whole bunch of antennas picking it up. So think about this and all those things we just talked about. We have capacitive coupling in the cabling. We have inductive coupling. We have wires running over one another. It's a bad situation. So time for poll question 1, Chris, if you're online.
No problem. We are launching it now. There you go.
All right, cool. So I'd just like to poll the audience and, do any of you experience electrical noise issues in these measurements? And the options I made a little cheeky, but yes, we have lots of issues. Yes, but it's not an issue yet. No, we have a really good test stand, or no, I don't do testing. And I'll be really interested to see what you guys come back with. Because the reality of it is that, even if it's not a huge issue, it's likely an issue that's there. And there's always a better way to do a test cell. And, I think a lot of people have done a lot of really good work correcting those, but you never really know. And Chris, I don't know how much time you usually give these.
All right. Looks like the voting has all come in. We have about 70 respondents.
Cool.
And I will share results here.
Awesome. And to no surprise, we have a handful of people who don't test, and thank you guys for joining the testing seminar. I hope you learned something. Yes, but it's not an issue yet. The people with the good test stand, I'd love to come through and just see what your setup is. I'm always willing to learn. And yes, we have a lot of issues. I'm not too surprised at. So I hope you guys can take away from stuff. Go to your labs, make some improvements, and again, HPK is here to help if you want to go down the rabbit hole. So with that, we'll jump into the good stuff. All right. So EMC, new issues. So those of you who didn't have issues, I think you're going to move into that oh shit category. We have battery voltages creeping higher and higher. And the graphic on the right is just a list of companies that have announced and introduced vehicles with 800-volt architecture. Historically, we had that 400-volt architecture, and things are creeping up. And there's great reasons for this, and we're not going to get into those. HBK's got plenty of videos on that if you're interested. But where I see it from the EMC is, remember I talked about that DVDT. Inverters go from zero to inverter voltage and from inverter voltage to zero very quickly. So if we look at this equation, that V going up increases our DVDT. Capacitances we had in our old cabling now are more apparent. So our voltage increasing, this battery voltage increasing, is going to increase my DVDT, my susceptibility to EMC, EMI. So this is scary. And if you're in aerospace or you're in agriculture, those voltages are talking even higher. If you're in, heavy trucks, Class 8 trucks, those voltages are talking even higher. This is going to keep being an issue. So that's scary thing one. Scary thing two. This is what scares me as a measurement person. Measurement problems keep you up at night. But it also keeps me employed. Wide bandgap switches. So this is your silicon carbide, your gallium nitride. And here I just have a graphic of an inverter turn off. So we go from the voltage being high to the voltage being off in a short period of time. The current flowing to the current being off in a short period of time. And I took a manufacturer of IGBTs, silicon carbide and gallium nitride, just so I had consistent data sheets. And I looked at their turn on time, their voltage, their DVDT spec, and their DIDT spec. And what we see is that the IGBT turn on time, 1,000 nanoseconds, 1,200 volts, 3.4 volts per nanosecond, 8.7 amps per nanosecond. It's fast, but not scary. Silicon carbide. A lot of the inverter manufacturers, a lot of the automotive companies are going to silicon carbide. Our turn on time is 50 nanoseconds. That's about 2 orders of magnitude less. 1,200 volts, same voltage. 10 volts per nanosecond. 10 amps per nanosecond. Order of magnitude more DVDT. And then there's gallium nitride. And while these are saved for smaller devices right now, I certainly think with the large amount of inverters that are going into active suspension, into all parts of the vehicle, especially with 48-volt systems, we're going to see more gallium nitride because it's great. A lot of advantages. 6.3 nanosecond turn on time. That's another order of magnitude faster. 650 volts, a little lower. 200 volts per nanosecond, 150 amps per nanosecond. These are blaringly fast. And this is all going to result in increased EMI. If we remember our DVDT, our T goes down, our DVDT and our DIDT go up. More EMC, more EMI. And just to really beat that point home, here's our two equations again. V equals LDIDT, I equals CdVDT. Battery voltage increases. We also have safety issues with that. So that's a different story. Our DVD goes up. Silicon carbide, gallium nitride switches are fast. Our DT goes down. Really hardcore math here, guys, I know. And long cables create capacitance. Loops are inductive. These are this L and C. Power levels are naturally increasing. DI goes up. So what we see is an increase in DIDT, an increase in DVDT. There's a lot more chance for that induced noise on the measurement cables. So what can we control as test engineers? What's the hopeful side of things? And the hopeful side of things is that we can control some stuff. We can control this inductance and capacitance of our measurement side. What the engineers do, the engineers are going to give us this stuff and we have to deal with it. I know. Engineers, think about the people doing the testing. But we can control the L and the C of our cabling. Parallel paths, we can eliminate those. Loops of cable, we can eliminate those. Distance between cables, we can increase that. Maybe. These are the things we can control. So we have to think about how do we reduce that inductance? How do we reduce that capacitance to get better measurements? New powertrain are difficult to measure. We're all going to have jobs. And just to beat that home, everything is more extreme in this circuit. This is back to my noise circuit, right? The distances, the 1 over R squared, so the distances between the measurement and the noise producer, so the inverter cables, needs to increase. And the scary part is that the same room, if you have the same test cell, you need more distance between your cables for these new inverters. Like if you walk into the same room that was an engine cell, and then you upgraded it to a electric cell, and now you have SiC coming in or GaN coming in, you might want to just reevaluate some of your layouts. And now you have the, what is it, Occam's razor of, well, now I have longer cables to make longer distance. So we might have some solutions for that. Currents induced in shields and grounds are higher. So these shields are still working, but now they're picking up more of that induced current. This is an issue because those grounding paths that used to be good aren't sufficient anymore. The shields that used to be good might not be sufficient anymore. The same test cell might experience issues you did not have previously. And I'm going to beat this horse, but high frequencies make the old cabling routes problematic, and that's just the reality. So we've covered the background, we've covered the new issues. Let's get into some of the solutions. So let's be proactive on this. So test cell layout, and this isn't going to be anything overly complicated. But we have our device under test power supply, we have our current measurement, we have our test inverter, we have our three-phase current measurements, our device under test, our motor, our torque sensor, our load machine, and our power supply. And in an ideal setting, we want all of these cabling routes to be pretty separate. We want to avoid parallel paths, we want to avoid loops of cable, we want to make everything as short as possible. So in your ideal layout, you actually have these things almost on opposite sides of the room. You want to increase that distance. You want your measurement cables to never be crossing your current carriers, because we want to avoid those cross sections. And if we have to have them crossing or close to each other, we want to avoid parallel paths. We want to have things crossing at 90 degrees. And that's kind of like some old school circuit layout stuff. If you have to have something close, make it close for a short distance and bring that back to your measurement unit. Have those be as short as possible. Same goes for the torque and speed cables. Have those not running in parallel with anything. If you have CAN bus temperatures, avoid parallel paths because those are going to pick up noise and could result in grounding issues. So avoid loops, make your cables as short as possible, avoid parallel paths. Create Faraday cages. We'll touch on this a little bit later, and we have some YouTube videos on details of this, but basically complete your shielding path and really look at your grounding, especially if you're having a lot of issues creeping up. If you have instrument grounds, use them. Make sure you have a really good grounding path. Use your braided cables for shielding. Use really low resistance shields, a grounding shield. So there's some stuff you can do just in layout. And if you roll in the instrument rack in, just have this stuff in mind. Cabling best practices. If you look at a current measurement, your conductor coming from your inverter usually has the conductor kind of in my light orange. You have a shield around it. And if you want to run this whole thing through the current sensor, I highly advise against it because you need that shield. That shield's going to be picking up those fields. It's going to be protecting that inverter cable. Whatever you run through the current sensor, you're going to be picking up all the currents there. So if you have a current in your conductor and a current in your shield, you're going to pick up the addition of those or the difference of those. So the measured current is going to be the conductor, the cable, plus the shield. And trust me, you have more current running in that shield than you think. And for example, if I have 100 amps going in this direction and I have 1 amp going in that direction, I'm measuring 99 amps. I'm off 1% just because I routed my shield incorrectly. But you might be saying, but if I take that shield off, I'm going to get noise on my measurement or I'm going to break that path. And you are correct. So how do we approach this? How do we get the good measurement and the noise immunity? Well, we start with a really nice shielded cabinet. You want an instrument grade cabinet, metal enclosure with the door grounded in a good grounding path from the cabinet to your ground plane. And this guy's going to act as your shield for your measurement. Now we go inside the box and we're going to route the shield around the current sensor. So we're going to have the conductor going through. We're going to have the shield routed around. So we have all the benefits of the shield. We now have the cabinet acting as the shield to protect it from bad measurements. And we complete that shield path so that the inverter is happy, so that the inverter can do its thing the way it expects. This is really the best way to do a measurement. You want the sensors in the cabinet. You want the sensors to be appropriately grounded. Sensors have a space They need to be a certain distance apart. So there's a space specification. Straight cables through the sensor is a good practice. You don't want curves, you don't want arcs. And if you can, keep your DC and AC signals separate. But just putting them in that cabinet, routing the shield around will really increase your measurement quality. We separate our shield current from our conductor. We can get good efficiencies, good power, good measurements. And what that looks like is we got a cabinet for our DC, a cabinet for our AC. They're spaced appropriately. We got those shields going around, and we're going to get really good measurements from this. The people who implement this have a notable increase in their measurement quality right away. Use good cables. Pay for the expensive cables. I cannot stress that enough. That $100 cable is going to save you so much headache over that $12 cable you cannot imagine. And at HBK, we do try to make this pretty easy. So our current sensors, we have a cable that goes from our current sensor to our amplifier box, and then we have another cable that goes from our amplifier box to our power analyzer. This is really going to make a good Faraday cage. It's going to make a good shielding path, and you're going to be really confident that you're going to get a good measurement. When you go to the actual cables, what makes up a good cable? Twisted pair, if it's a three-phase voltage, twisted thruple, are really good cables. You can get them individually shielded. You can get the whole thing shielded. Shield your voltage cables. Have your current cables shielded. Don't just go bare wire without a shield, because you will have headaches. Because you want to keep that noise in and you want to keep other noise out. You want to protect it on both sides. Pay for the expensive cables. All right. Now, sample rates and filtering might seem a little off topic, but they're not. And I hope you see why in a moment. So people always ask me, what should I sample at? And there's a lot of questions to ask before I answer that. But first and foremost, like, what are your events of interest? Because that's going to determine what type of instrument you use. Are you looking at real detailed switching events? Maybe then you need 100 megahertz or a scope. Are you looking at power? Now you need to consider accuracy versus frequency. And spoiler alert, power isn't the fundamental, so you don't need that high of a sample rate. Are you looking at faults? Are you looking at that type of thing? That's the higher sample rate too. So you need to balance that. What am I looking at? What signals am I trying to measure? Am I just looking at the signals? Do I just want control type stuff? Do I just want to see my modulation scheme? Or am I looking at calculations, power, reactive power, apparent power? These things, they have different requirements for sample rate. What are your accuracy requirements? And the most important one is, what is the bandwidth you want to see? If you don't know the answer to that, you got to find that answer first. And certainly people like HBK are willing to help you talk through that. But especially if you're a test guy and you get assigned a measurement, like, ask the engineers, what bandwidth do you want to see? And if they don't know, let's have a conversation. So first question. Second question, why are we filtering? Are we just doing anti-aliasing? Cool. We'd help you with that. Am I trying to clean up my measurement from noise? And this is where the relation comes in, because the noise that you're experiencing might not be noise. And if you clean up all of your cabling, you might just be looking at signal. You might just have really nasty switches. And the last one is, because we get values we don't expect. And this comes into a different problem, and HBK's got a lot of videos on this. But your RMS, your reactive power, your power factor, those are tied to the frequency content. So if you're getting a value you don't expect in your calculation, you need to ask yourself, what's the bandwidth of calculation I want? So think about these things. And the scary thing is if you filter down to get an RMS value you want, you might eliminate some power. So think about, what's the bandwidth I need for power? What's the bandwidth my engineers want to see for things like RMS? These are questions they might have answers to, because it's things people don't think about, especially when they live in MATLAB and they say, put a filter somewhere, and they never think about it. Got to ask yourself, what are the bandwidths we want for our different calculations? And on the right-hand side, I just have 3 examples of the exact same signal. So we have a 50 kilohertz bandwidth where we have these nice PWMs and this current. And here's my power at 50 kilohertz. It's nonsense, because you need to average power to get a good value. 10 kilohertz. All right, now we get pretty smooth sine waves. We still get a little bit of voltage. And now my power is a little more sane. And then fundamental, where we eliminate all the high frequency content. What do we want to look at? That's not an answer for today. we'll shed a little more light on this. But if you have questions on like what do you want to look at, what frequency do you want to know, please reach out, because these are really interesting topics that are not intuitive, that people don't think about. So why are we filtering? And if the answer is to clean up the measurement from noise, but we did a good job with the cabling, we have to ask ourselves, well, am I doing more harm than good? Because noise is in the frequency range of the inverter. The inverter is creating the noise, but I also want to catch things from the inverter. So which one of these do I want to look at? Do I want to look at the filtered? Do I want to look at the unfiltered? And the issue becomes that filter suppresses amplitudes and alter signals and calculations. So that's when we come back to bandwidth. What's the bandwidth we want to see? And ask yourself, is it noise or is it the inverter? Do I understand my signal? Do I understand my calculations? Because once we start solving those noise issues, we might have different problems we need to solve. And it's understanding how our calculations are done, how our measurements done. We've got a whole bunch of videos on that. We can take that offline. If you have questions, please reach out. But this is really important stuff, because once you solve the cabling, once you solve the EMI, now you get to have the fun problems of what are the bandwidths, what are the calculations. Just a couple notes on electric power. Inverter signals happen quickly. You need a high sampling rate, 200 kilohertz to a megahertz to get good power information. This isn't going to be switch analysis, but this is going to get you the power, because you want to have that inverter happening. Don't attenuate out your inverter. Power, if you're looking at power, it's contained in the fundamental and its harmonics. So don't filter below your current or your power carrying harmonics. If you look at the fifth harmonic or the seventh harmonic on a really fast machine, so let's say your fundamental frequency is a kilohertz, your fifth harmonic's 5 kilohertz, your seventh is 7 kilohertz. You have a 3 kilohertz filter, you're eliminating power. You might see efficiencies higher than you expect. That's bad. Again, not a noise issue, but if you're filtering because you think you have noise, you're altering your signal unintentionally. And now these calculations. A lot of times people are like, my reactive power is gigantic. It's a calculated value. You have to ask yourself, am I using the right calculation? Because your engineer probably wants to see the fundamental, which is eliminate all of the harmonics, just fundamental. So something to think about. What bandwidth do I need for which signal? Because once you eliminate the noise, now you start getting into the measurement. All right. I'm doing okay on time, so I might go through this quickly, but we're going to share these slides because this is some practical hints on switching rates and filterings. So for a power measurement, I'd say have your sample rate about 10x your switching frequency to get that switching information. You want that for the power, but you don't need all the super high frequency details because no power transmits in that. You want to have the bandwidth of interest. Filter 2 times above your highest harmonic of interest, because electrical power, again, this is all for power. Electrical power is carried in the fundamental and its harmonics. If your highest harmonic of interest is the 20th harmonic, take your highest speed times 20 times 2, and you'll have a pretty good measurement. But please note, current sensors are the limiting bandwidth, so don't set your filter above your current sensor. There's no point. Consider the bandwidth you want for your calculations, for your power, for your fundamentals, for your PQ, S, RMS. Consider your measurement uncertainty. Don't try to calculate things that are impossible. If somebody asks you to calculate iron losses, really sit down and say, hey, instruments aren't that accurate most of the time. And use the same filters on all channels. And this is a big mistake that people make. Set everything the same. Voltage, current, DC, AC, all your filters the same. That'll help a good measurement quality. Now, for you test guys, once you start asking these questions, you need to start asking your engineers some questions to get the good measurement. So don't be afraid to ask your engineer, what's your switching rate? So you can go back to my slide before and give some good advice. What's the bandwidth you operate your models at? That'll help you have consistency between MATLAB and measurement. What's the bandwidth of interest for those different signals? Power, RMS, Q. What's your max fundamental frequency? And don't be surprised if your engineers give you conflicting information. Ask more questions. Dig into this. because everybody might learn about measurement and we might get to, some really consistent good results faster. So once we've solved the EMC issues, we can say, all right, we don't need to filter the hell out of our signals anymore. Let's get to good measurements, good calculations. Here's a super practical. You guys can read that on your own. Now into the what I think is the fun stuff, because this is some new products from HBK that I think are going to help eliminate a lot of these issues, even if you can't, especially if you're limited in space, especially if you're limited in your cable routing. So let's review. What are the effects of our interference? What are the dependencies? Voltage level, current level, frequency of the inverter. Those aren't going away. Unfortunately, those are from the engineers. But parallel paths, distance, and shielding are things we can affect. And we have to ask ourselves, what if we eliminate copper from our measurement? And that's where this whole fiber optic idea comes in. Because if we eliminate this copper, we eliminate all these couplings. And when we eliminate the couplings, we eliminate noise. So kind of coming to this super practical, this is an ideal power analyzer setup today. We got our battery, inverter, motor, gearbox, transmission load, whatever it is. We got our current sensors. We got 4 cables coming to a CT power supply and 4 more cables coming to a power analyzer. So we got 8 cables. I'm in Japan right now, so it's 8. We have 4 voltage cables and, torque and a speed. And in the ideal setting, this is still a lot of cables. But in reality, we have setups that look like this. We've got, this nightmare. We've got unshielded things everywhere. We've got just stuff lying on top of each other, next to each other, loops of cable. This is the reality we deal with. So we go back to the screen, 12 cables. We got 12 cables of voltage and current, 2 more of torque and speed. Well, we have high voltages too. We have to consider these voltages are going higher. We have high voltage safety issues. High voltage can potentially come back to the automation system, come back to the control room. So we got high voltage. So you want to make sure your stuff's cat rated appropriately. It's not the topic of today, but it's also important because safety is a factor too. We have EMC issues. These high voltages and these currents are right next to each other. They're right next to the inverter lines. We have EMC issues up here. Now, this is a low, or a low voltage, low current cable. You have a lot of potential for signal to noise, and that's coming in right next to a high voltage or a high current. This isn't just HBK. This is every instrument you're ever going to touch. Another view of that same test setup. High voltage is coming in, long cables. These cables can potentially be quite long, a couple meters. We have long 8 cables coming from our current sensor to our power supply to our power analyzer. And a lot of potential for noise. So here's our proposal. And here's the new product we're coming out with. We call them the fiber optic probes. We're going to have a box that sits right next to the measurement. This box is going to measure voltages, my box on top, or currents, my box on the bottom. And it's going to sit right next to the measurement. You're still going to have a copper measurement cable, but it could be 10, 20 centimeters, really short. We shorten that cable. We shorten that inductance. We shorten those parallel paths. We shorten those loop paths. We shorten all of this stuff. 10 centimeters, not much room for noise. We lower that L. We lower that C. We lower that induced noise. We digitize the signal out here and we send it back fiber optically. Same goes for the current. 10 centimeter current cable. We're now going to offer that power supply inside of the fiber probe. So we're going to do the excitation locally. Now, instead of 8 cables, we got 4 cables. Short, low L, low C, low induced noise. Boom, fiber optic. And once it's fiber optic, it's light. There's no copper. Remember my point about eliminating copper? Gone. Really clean measurement. What are the benefits of this? Well, uncompromised safety. You no longer have high voltages coming back to your control room. And if you really look at it, safety is the most important thing. HBK is all about safety. We have a safety briefing every day. So, safe, this is going to be as safe as it gets. No high voltages coming back. Minimize EMC. You reduce your inductance, reduce your capacitance, reduce your parallel paths, reduce your loops, reduce your EMI, EMC conduction in your measurement. Shorter cables prevent reflections. You actually get a higher quality measurement because you're now transmission line physics. You're getting rid of a lot of that because you have a very short cable. At the high inverter switching, at the high DIDT, this is real. I'm sure there's some guys from a certain automotive company who I've worked with who are going to be very elated because we've seen reflections in their measurements, and there's nothing we can do because it's in the cable. I mean, that's in the measurement cable, except make it shorter. Integrated CTs to minimize the amount of cabling. Fewer cables, less noise. That one's pretty straightforward. And because it's fiber optic, it's all light, we can put these up to 50 meters apart. Now, if you've got a test cell where you've got things really spread out, we can really spread things out. Multiple motors. I think of the aerospace guys who have stuff all over. This is a really, really exciting technology. So my old setup, lots of safety, lots of EMC. Still there. It's not completely eliminated, but we've shortened those cables. We've eliminated cables. We've made this a lot safer and better from an electrical noise standpoint for measurement. You're just making your measurements better. So some of the tech specs, the remote voltage probe, five voltage ranges up to 2 kV for those ever increasing voltages. And these are going to be available in 2 megasample and 20 megasample variants. So we can actually go to a higher sample rate for some internal technical reasons as well. If you want to start looking at some of those more detailed switches, to be honest with you, for power, you don't need much above a megasample. But if you feel that you do, that option's there. Current. We're going to have 6 current ranges up to plus or minus 2 amps. Again, 2 or 20 megasamples. And we're going to have an option with a built-in current power supply to simplify that cabling. And the last one's just our internal card. This is for bringing in the measurements. But, 4 voltage measurements, 4 current measurements. It's going to be a really sweet setup. 2 cables, 2 fiber optic cables. So just from the simplicity standpoint, it's going to simplify things a lot as well. Now it's time for poll question 2, Chris, if you're still on the line.
Coming right at you. Should see it now.
All right. And this is a simple one, and we'll see if anybody's awake still. Would fiber sensors simplify your setup? Yes, no, or sorry, I was asleep. And we're really hoping that this gets people excited and it really helps you solve some of those problems. And if you just want to talk over ways with traditional methods to simplify your cabling, we're here for that as well. But I think there should be a lot of interest in this.
All right. I will end the poll now and share the results.
All right. And quite a few of you think it would be helpful, and we're happy to hear about that, and we'd love to talk this over with you, and I hope some of you reach out, and we're more than happy to follow up on that and talk details. So, gonna click back. So just my conclusion for those of you who might be interested or just educationally, fiber optic eliminates those long copper cables. And loops, and loop the fiber cable all you want. Loop it like crazy. You can do whatever you want to that. It's super immune. Reduction of parallel paths. And this is the one that I'm personally most excited about because whenever you walk into a lab, you end up seeing a conduit that's got a CAN bus and a high voltage line running together. And the more of that we can eliminate, the better. We reduce the inductance and the capacitance of the lines. I spent a lot of time today talking about these capacitive and these inductive issues. And I did that because this is the savior for that. You can operate in a smaller test cell. And this one also gets me excited because the company is sure as hell not going to shell out more money for a big room. This helps you operate in the room you have. This is actually going to save you a bunch of cost on doing new labs or at least new infrastructure. And HBK can help you achieve better measurement, whether that's automotive test cell, where you've got your currents and voltages going back fiber optic, or aerospace, where you want to do a whole airframe with things spread out. We actually came up with this for aerospace and have way more interest from automotive, which I find fascinating. But you can spread things out. There's a whole bunch of cool stuff with calibration we do if anybody has calibration questions. And you can move the box from room to room and leave the probes in there and just hook up and go. So it could help your setup simplification as well. And lastly, we're 5 things plus noise immunity: data acquisition, power analysis, scope, results logger, and the API. And everything you've heard me talk about HBK before remains the same, just with that higher level of noise immunity. So with that, I'd like to thank everybody for sitting with us. You can find out more information about our products here. Please feel free to reach out to me on LinkedIn. It's Mitch Marks or Mitchell Marks. And yeah, hopefully we got some good questions coming in.
Great. Thanks, Mitch, for the presentation. We have about 15 minutes for the Q&A, which is good because we have a lot of questions coming in. If you
Cool.
click the Q&A button on your screen there, you should see them. Also, I'll post a link to download the slides in the chat box here. Got a
Cool.
few questions asking for those. So if you could just scroll through the questions and
Yeah.
read them aloud and then give your response, that'd be great.
Awesome. Yeah. And just give me a second here, and guys, please bear with me. Let's see. How are inverter EM waves shielded in a car? Do you offer testing to assess the effectiveness of EMI solutions? We do not offer kind of the EMI assessment like the traditional EMI chambers and the really high frequency stuff. We're really focused at the motor inverter power measurements. So in the vehicle, they have really nice shielding that's connected, but the benefit they have in the vehicle is that you can have those things really close together. So by having the motor and inverter coupled together or on top of each other or sharing bus bars, you can eliminate a lot of the noise issues transmitting to the vehicle. So in the measurement cell, you need to pop those things apart so you can measure those voltages and currents. So that's where a lot of these challenges come. So no, we don't do EMI assessment, kind of the traditional way. We offer measurement solutions to reduce EMI on high voltage, high current measurements. So thank you for the question. Just different area of expertise. All right, let's see. Question presented about the CT box. In the current transducer box, couldn't you just end the shielding in the box itself and not route it for each cable around the CT clamp? That very much depends on the inverter, and thank you, Max, for the question. Completing the shielding loop for the inverter is a lot of times you need that to make it function happily and function in its normal state. And also for the inverter's sake, you want to complete that shielding loop. So it'll be inverter to inverter, motor to motor. But best practice is to complete it the way it is in the vehicle as close as possible, which means having that shielding loop connected. And this is in reference to that current sensor box that I showed and routing the shield around the cable. So certainly you could terminate it, but you might have some other issues. So I advise routing the shield around. All right, next question. Let's see. Why reroute the cable through the sensor and not just cut the shield in the region of the capacity? The enclosure will protect it from the electrostatic interference. Very similar to the previous question. You don't just want to cut the shield because the inverter wants the shield to be happy and the inverter needs the shield so it can operate without noise itself. Back to the first question about how is shielding done in the vehicle. These cables have shields because they need to operate. The motor and inverter need their grounding path completed properly. They need to talk appropriately. So we want that shield path to be continued so that things don't get unhappy. And also to protect everything around the measurement. If we eliminate the shield from that cable's creating more EMC, EMI. So we want to keep everything in the cell happy, and routing that shield around the measurement, keeping it as close to how it would be in the vehicle as possible is really best for the test, the best for keeping things consistent, and the best for reducing the amount of noise in the neighborhood. How far away can the probes be positioned? Up to 50 meters. So you buy yourself quite a bit of room. And if you need to space things further than 50 meters, we have some clever ways of doing that with multiple mainframes and then the fiber as well. So the probes can be up to 50 meters apart. Good question. Does noise also affect the torque and accelerometer signals? It very much depends on what your signal is. But torque signals are usually a voltage or a frequency, which certainly can couple noise. Even a frequency, which is a digital signal, can couple noise, especially if there's grounding issues. It's a differential signal, so if you end up floating things, it can get a little gnarly. Um, so yes, and on the accelerometer signal, same question. You can corrupt that signal, and really the answer is it comes back to that shielding, it comes back to that grounding, and it comes back to that galvanic connection. You want to make sure you ground your torque sensors really well. That will help you eliminating that noise. You want to use a frequency output torque sensor. That's going to give you a digital signal, which is much higher quality. And for accelerometers, HBK actually offers some really cool accelerometers that are quite noise immune. It's basically through reducing the galvanic connection to the surface. So reducing that galvanic connection, having good grounding, these signals are certainly susceptible to noise. HBK's got frequency-based torque sensors and some really nice accelerometers for eliminating that noise that you might see. Should you ask who is already using fiber? I'd love to know who all is using fiber already. Mike, I don't think there's too many fiber offerings out there at the accuracy level we have. But if you've got it, I'm quite interested in it. All right. Why do the remote current probes have such a small current rating? Great question. The most accurate way to get a current measurement is with a flux gate based sensor. So our sensors are really, or excuse me, our measurement tools are really made for taking the output of those flux gate based sensors. You usually take a sacrifice in bandwidth and accuracy, taking a direct current measurement. And usually those have some sort of shunt involved, which alters the signal. So by using the current sensor, you're not interrupting that current path. You are not introducing a resistance to measure that current. So really, the 2 amps is to take the output of a current sensor. It'll also take plus or minus 10 volts if you have a voltage output for Gauss coils or something like that. But using the current sensor is really the most accurate way and the best way to go to high currents. So we like the current sensors. It's the highest accuracy path. All right. Linda, thank you for your nice comment. Let's see. Is there a minimum sample rate to capture to be able to use that's a technical support specific question. We could certainly reach out to you, anonymous attendee. If you get back to me with your name, you asked a question about the e-Power Suite, I'd be happy to get back to you or have someone on our team. But you were anonymous, so I don't know how to help you. So please, if you were anonymous and left a comment about the e-Power Suite, just drop your name and we'll get back to you. Mike again. Does cable shielding actually help? Some of our recent tests suggest it causes more problem than it fixes sometimes. Certainly, but this is probably coming back to your shielding, or excuse me, your grounding path. So if you're having issues where shielding is not helping things, really sit down and look at the path to ground of everything, because you likely have some sort of loop going on. And if it's measurement shields, you could be creating ground loops. If it's the shield of your inverter cable, you might want to bring your engineers in and figure that out. Because certainly putting a shield in the wrong place will create a galvanic connection. Now you have loops, now you have floating grounds, and now you have problems. So you just want to look at your grounding path, at your shielding path, and make sure you're creating your Faraday cages and you're not using something somewhere else. So I can't answer that because I don't know the exact situation. Everybody's a little different. But certainly that means you've got an issue going on, which is something you should probably dig into in your grounding plan. How do costs compare to current sensors? I assume this question is in regards to the fiber probes. They're not actually that much more. I don't want to give a number here because our prices vary region to region, but it's going to be about 15% more. but you get a lot with that, the high voltage safety, the noise immunity. So again, would be happy to take that offline. And if you're interested, please drop a comment or hit me up on LinkedIn or email. And we'd be happy to put you in touch with our application and sales team. All right. How much for test engineer services? How much for the fiber unit? Trong, again, I'll if your email is listed, we'll certainly get back to you on pricing. We don't offer that many engineering services, but it depends what you're looking for. Certainly things like grounding and EMC are in the area we would offer some services for. So I'll reach out after this, and again, please drop your email and the questions, and we can make sure we get back to you. All right. Nicholas, do you sell any protecting boxes with the right connectors for spinning the shield wire through the box to preserve the continuity of shielding? Nicholas, we have a custom solutions team that can certainly provide those boxes, and we would take into account your specific needs, and they would be able to fabricate a really nice box for you. So again, if you drop your email, we'd be happy to reach out. We do offer some custom systems, custom sensors for these types of enclosures. So certainly, we do it the very German, the very right way. So it'll definitely fit your solution. So it's not off the shelf, but we do that, and we do it quite well. All right. So from John, due to the higher voltages that will be seen in electric vehicles and higher switching frequencies seen with wideband gap semiconductors like GaN, will the EMC shielding on commercially available high voltage wires used in current EVs be adequate, or will new wire with improved shielding be needed? For the measurement cables, and I'm going to speak to the measurement cables, I'm sure in vehicle, there's definitely some considerations for the high frequency, high voltages. That's more of a safety UL concern, is my understanding. On the measurement side, yes. We are going to have special high voltage cables that have really special shielding for making the high quality measurements and hitting the safety specifications. So we really need to stress the safety as we go to higher voltages, higher currents. Yeah. So there's going to be new cables coming out. We actually are going to have to fabricate them ourselves, I believe, because they're not necessarily always commercially available. So please stay tuned. We'll have, again, some very, very good cables coming out that have the shielding you need. I have a question coming in. What are the fundamental frequency calculations specifically? That will be in the presentation we share. But the fundamental frequency is basically your frequency of rotation times your poles over 2. And then the number of harmonics of that is speed of rotation times pole over 2 times harmonic. So that I hope that answers the question. Yeah, your engineer should know, or speed of rotation times poles divided by 2 is your fundamental frequency.
Hey, Mitch, we have time for one more question.
All right. Okay. So I got a question from Constantine. He asked it twice. So I'll try to answer. Does it make sense to also use ferrites for the sensor wires? Ferrites can certainly make sense, especially on digital signals. It doesn't hurt anything. It's basically helping eliminate some of that noise. So it doesn't hurt anything. You're introducing loops typically to do it. So I would say really focus on the cable layout for power carriers. For digital signals, life's a little different. So yeah, thank you, Chris. And the questions I didn't get to, we will certainly try to answer.
Yeah, thank you so much for the presentation. Thanks everyone for attending and submitting all the great questions. It was a very good conversation. As I mentioned earlier, a recording of the video will be available to view on demand, so you can visit the session registration page. You can also find a link to download the slides there, and there's a contact form where you can send more questions to Mitch. And of course, please feel free to share the link with any colleagues that were not able to attend today. So thanks everyone for taking time to attend, and we hope you all found it valuable. Thanks, Mitch.
Thank you, everybody. And thank you, Chris and Charged. Always a pleasure.